Maybe the just to check can you share your screen for your slide or
Sure.
yeah,
I'm co-host. I'm allowed?
maybe
Ah, okay.
yeah,
Great.
okay,
Um,
perfect, yeah. I think the maybe some faculty member in our university is not possible to come this seminar because it's
too
originally
early.
our seminar starting from the 4 half past 4 p.m. but because of the time difference between Miami and here, so we are starting the early morning. So some I think people has their class this time. Yeah.
Ah, okay. Sorry about that.
No, no problem. I just wanted to hear from you about this. Actually, I tried to, yeah, I read some your maybe first paper about this direction, but didn't study everything. So maybe it's the best thing is to just to directly hear from you.
Okay, sure. And if you have any you or anyone else has any questions, please
Yeah,
feel free to jump
no
in.
problem. Yeah, I will. Yeah. Also here, some audience also will do. Yeah. I think the yeah people is coming and coming, but because the time done, so I would like to introduce. Okay. I'm very pleased introduce today's speaker. Is the Rafael Nepomechie from University of Miami. He is a leading expert in integrability and also made some important achievement on spin chains and exact asymmetrics. More recently, he has been working on problems applying spin chain, Bethe, and such to quantum computer research. So I think that he is also going to talk about that today. So the title today is the Bethe state preparation, and please start, Rafael.
Okay, Minkyu, thank you very much for the invitation and for the introduction. It's wonderful to be back in Korea, even if it's just virtual. Um, so yeah, please, if at any point you have any questions or you have any comments, feel free to just jump in. Um, so actually, before I begin, I'd like to take a moment to remember Chaiho. I was very sad to hear that he passed away recently. So I actually wrote a paper with Chaiho before we met. This was back in '87. This is him and this is me. And we shared Lowell Brown as a mentor at the University of Washington. But by the time he wrote the paper, I had already moved to Miami.
I see.
So we didn't meet until many years later. So this was in post-tech uh, in 2003. And then, but then afterwards, we met many more times. This photo here, maybe some of the audience is in the photo, was at a conference that he co-organized at Sogang, and a very nice conference, Zamological. Chaiho was very kind. He had a wonderful sense of humor, and it was always a pleasure to meet with him. Okay, so the work I'm going to report today was done together with actually an undergraduate student, David Rave, who's now moving to graduate school in Rutgers. So by way of introduction, an interesting problem in quantum computing is a so-called quantum state preparation problem, which is how to prepare a given quantum state, say an eigenstate of a Hamiltonian, on a quantum computer. And this could have interesting applications. For example, once you have this state on your quantum computer, you could then compute correlation functions, compute the entanglement entropy, and so on. So, well, what will be an interesting eigenstate to prepare? Well, an attractive candidate would be a Bethe state. That is an eigenstate of an integrable Hamiltonian. That's because such states are better understood than eigenstates of non-integrable Hamiltonians, at least usually. And also these are can be highly non-trivial states. And so the goal of today's talk is to present to you an algorithm for preparing Bethe states, that is exact eigenstates of the Heisenberg quantum spin chain. And this is work I did with David recently. So here's an outline for the remainder of the talk. Since it may not be familiar to everyone, I'll begin with a brief review of Bethe ansatz. And then since it also may not be familiar to everyone, I'll also have a brief review of quantum computing. And then it turns out that it's a nice warm-up before getting to Bethe states to prepare simpler states called Dicke states. And so I'll tell you a little bit about that. And then finally, we'll get to the Bethe states, and then conclude with a brief outlook. Okay, so let's begin with our review of Bethe ansatz. So to be specific, let's work with probably the most paradigmatic integrable model, the closed isotropic, or XXX spin-a-half Heisenberg quantum spin chain. So it's a big mouthful, but it's really a deceptively simple model of magnetism that was put forward by Heisenberg back during the dawn of quantum mechanics. And so it describes a system of L spin-a-half spins arranged, say, in a circle, in the case of the closed chain. And then each spin interacts isotropically with its nearest neighbor. So say this guy with the one to the left and the one to the right. This is a Hamiltonian describing this system. So let me explain the notation. Here, sigma L plus 1 is identified as sigma 1. So this is enforcing the periodic boundary conditions, the fact that we're on a circle. And then this subscript n tells on which site this sigma operator is acting. So here we have tensor products where the sigmas are the familiar Pauli matrices, sigma x, sigma y, sigma z. And this guy here is the 2x2 identity matrix. So we label the sites 1 through L, and everywhere it's identity except at site n, where it's sigma. And this dot means I should sum over J from 1 to 3. Okay, so I hope this notation is clear. And so you see that because we have these tensor products of two-dimensional vector spaces, this is a 2 to the L by 2 to the L matrix. And this model of magnetism can be realized experimentally. It has connections with conformal field theory, with ADS-CFT. In fact, I would say that this is one of the most fundamental models in theoretical physics. It appears in many, many contexts. And one question you could ask is, what are the eigenvalues and eigenvectors of this big matrix? So if you try to do it on a computer, you can't do too many sites because the size of the matrix is growing exponentially. So this kind of brute force approach won't get you very far. So it turns out just a few years after Heisenberg wrote down his model, uh, Hans Bethe found a solution. And it's really quite remarkable. It's known now as coordinate beta ansatz. And what he did is he reduced this very difficult problem to solving a system of polynomial equations. And these equations are known as beta equations. So it's still, there's still something left to do. You still have to solve these equations, but at least it's simpler than diagonalizing these huge matrices. So let me walk you through this coordinate beta ansatz solution. The main point is that the eigenvectors are multi-particle or multi-magnon states. So in the case of no particles, that's the ground state. So this state is given by basically all the spins pointing up. In other words, it's the L-fold tensor product of 1, 0. So turns out we engineered the Hamiltonian such that this guy is indeed an eigenvector with eigenvalue 0. Okay, so now the one particle state you can form by flipping one of these L spins, say at position x, and then you weight it with a factor e to the ikx, and then you sum over all positions x. We'll call this psi of k. And it turns out this vector is indeed an eigenvector of the Hamiltonian I showed you earlier, where the eigenvalue, little e, depends on this k and is given by this formula. So we can think of this as the one particle energy. Now, it's not true for any k, it's only true for k's that satisfy this equation, e to the ikl is equal to 1. Okay, so now let's turn to the two particle states. So now what we do is we flip spins at position x1 and position x2. We weight it by this factor here, and then we sum over all positions x1 and x2. So this factor here, s, depends on two k's, k1 and k2, or k and k prime is given by this formula. So it has this s factor and also a phase factor here, e to the ikx. And notice that this term here goes to this one if we interchange k1 and k2. And you can think of the ratio of these little s's, which I'll define as big S, as the two particle scattering matrix between these two particles. So think of K as the momentum or quasi-momentum of the particles, and they scatter in this one space and one time dimension, and this is their scattering matrix. And it turns out that this state here is indeed an eigenstate of the Heisenberg Hamiltonian, where the energy is simply the sum of the two one particle energies. And again, that's true provided these quasi-momenta, K1 and K2, satisfy this set of equations, where again, S is given here in terms of K. Okay, so that's our two particle state. And then finally, the general M particle state. So now, as before, now we're going to flip M spins. So at positions x1, x2, all the way to xm. We're going to weight it with this weight I'll explain in a minute. And then we sum over all possible positions of these flipped spins, x1 to xm. Now here, we you remember in the case of two particles, these two terms could get one from the other by permuting K1 and K2. Now we sum over all permutations of 1 to m, and then here we have the permuted k's, and here we have this phase factor e to the I kx, and then this factor a here is a product of the little s's I defined on the previous slide. And this epsilon is the signature of the permutation, so it's plus or minus 1. And then it turns out that this state is indeed an eigenstate of the Heisenberg Hamiltonian. The eigenvalue is just the sum of all the one particle energies. And that'll be true provided these quasi-momenta satisfy this system of equations. So we have, excuse me, m unknowns because we have these m quasi-momenta. So we have m equations for m unknowns. And these equations are what are known as the Bethe equations. And this state here is the Bethe state. And I emphasize this is an exact result, no approximations. It's quite remarkable. And if we change variables, if we go instead of working with k, we work with u, defined this way, and define uj to be u of kj, then the Bethe equations can take this form. And if you cross multiply, then you recognize this as a system of polynomial equations. So indeed, so if you
Sorry.
can solve this, yeah, please,
May I ask a question? So maybe,
please.
yeah, thanks. Maybe this is why you said quasi-momentum, but I was a little bit confused because the original Hamiltonian is written in terms of this sigma vector, the Pauli matrices. So I guess that represent literally the spin, but I didn't see any kinetic terms like considering the movement of spin. So when you say momentum k and location
Yeah,
x,
that's right.
so I was a bit confused what that actually means.
Yeah, so right, it's not so because it's a spin chain, we don't have translational invariance,
Yeah,
right? It's a discrete system. So the symmetry we have is it's invariant under translations by one site,
right.
right? So you can define a one site translation operator, and then think of this as so it'll be a unitary matrix. So in the case of continuous space-time, that you'd have a translation operator which is e to the I say x dot p,
Right,
which would
I
be a
see.
translation by x, right? Where x is some c number and p is a momentum operator. Well, here you can define this. You can define a one-site shift operator, and you can think of it as u is equal to the e to the I p, where p is a quasi-momentum operator,
Yeah, that
right?
now I understand. Yeah,
And somehow this would be like the eigenstates of so eigenvalues of this
yeah,
quasi-momentum operator.
good. Thank you.
Yeah, yeah, good question. Yeah,
Excuse me. So I have a related question.
yeah, please.
So the dimension of a Hilbert space to be 2 to the L. So should
Exactly.
mean that there are a finite number of solutions for this discrete number K.
Very good.
Yeah, and so I want to know this Bethe solution provide complete set of eigenfunctions, eigenstates or not?
Yeah, great question. So I'm not sure this, I mean, I think the answer is yes, but I don't think there's a proof. So so maybe so there may be a proof, I'm not sure. There's been some debate about this, but there may be a proof. Let me leave it like that. But certainly as far as we checked, it's complete. And I'm going to comment a little bit about this more in a minute. But yeah, for
Okay, yeah,
yeah, so I think it's believed to be complete.
I see. So
For
one
the rational case, it is really yes, yeah. I think it provides complete set of,
so in
but
the
for the
maximal
other
case,
case, I don't know. Yeah, maybe Rafael should know more.
is it in the
Sorry,
maximal case where M is equal to large L? Is the energy still zero there?
is the energy zero? So actually, it turns out, and I'll explain it, and I'll mention in the next slide, I think, that actually the maximal case is actually M is L over 2. But
I see.
what was your, I didn't catch the rest of your question.
No, I just want to know because it looks like there are two ground state. I thought initially, all spin up, all spin down.
Actually, there's more than that. So, okay, so
Okay,
let me
yeah,
let me comment on this a little more. So that'll be actually the next slide.
thank you.
So the point is that this model has SU2 symmetry, and therefore there's a degeneracy, which is L minus 2m plus 1. Yeah, I didn't prepare a slide, but so I can maybe explain in words that it turns out that these beta states are SU2 highest weight states. So if you apply the spin raising operator, it's annihilated, right? So so then from every beta state, you can act with the spin lowering operator and get additional states which have the same energy, right? Because the spin lowering operator commutes with the Hamiltonian, and because the highest weight state turns out it has spin um, uh, L minus m over 2, then the degeneracy is 2s plus 1, which is L minus 2m plus 1. So actually, this ground state is the one with m equals 0, right? So it has degeneracy L plus 1.
Thank you.
And then the highest one, when m is equal to L over 2, that's a singlet. Yeah, so we'll see this in an example in a minute. Yeah, so it turns out also from SU2 symmetry, you can restrict the number of overturned spins to be less than or equal to L over 2. So yeah, to make it clear, let's look at an example. So a simple example where I have just 4 spins, okay, L equals 4. So according to this, we should consider M as 0, 1, and 2, right? Because the highest number is half L, and L is 4. So let's organize the results in a table. So in this column, I'll put the value of M. This column, the beta roots. Here, the energy, using the formulas I showed earlier, in the degeneracy computed with this formula here. So when M is 0, okay, we have no beta roots, and we said that the energy is 0. And according to here, when M is 0, the degeneracy is L plus 1, so it's 5. So we have 5 states with energy. So we have like 5 ground states that are degenerate. Now, when M equals 1, it turns out that there are 3 solutions of the beta equations, which in terms of U read 1/2, -1/2, and 0. And so for each value of U or K, the quasi-momentum, we can compute the energy. It turns out this guy has energy 2, this one has 2, this has energy 4. And each of these had degeneracy according to here, 4 minus 2 plus 1, so 3. So we'll have three energy twos, another 3 energy twos, and then 3 energy 4. And finally, when m is 2, the highest value, it turns out there's two sets of solutions of the Bethe equations, plus minus I over 2 and plus minus 1 over 2 root 3. And then if you evaluate the corresponding energy, this one has energy 2 and this one has energy 6. And according to this formula, these are singlets. And so so this is going to be the highest energy state, and this is going to be the ground state. And if you add up these numbers, you see that you get 16, which is 2 to the 4, which is 2 to the L. So it shows that the Bethe ansatz is complete in the sense that we were able to get all the states, if you include these states that we get with SU2 symmetry. And also, if you would sit down, say, with Mathematica and just write down the 16 by 16 Hamiltonian and ask for the eigenvalues, you'll get exactly these eigenvalues with these degeneracies. So it agrees with exact diagonalization, and it shows that at least up to L equals 4, the Bethe ansatz is complete. So did that answer a little bit the question about completeness?
Yes, thank you. Yeah, at least for this
Okay.
example. Yes, yeah, thank you.
Yeah. Okay. Great. Okay, and it should work like this for any L. Okay, so this concludes the review of Bethe ansatz. If there's any other questions, okay, then let's turn to a review of quantum computing. So a qubit is a two-state system, and in this quantum computing business, it's conventional to call the basis states 0 and 1. So 0 is this guy and 1 is this guy. So the basis for a qubit. And then a quantum computer, I'll define it as a device that has n qubits, and I'll say later what n is. And then, so the basis will just be tensor product of these qubit basis. So xj here are either 0 or 1. So we're talking about, again, this basis states. And so you can think of this guy here, these as the binary bits of the integer x. So xj 0 or 1 times 2 to the j, this gives you the binary representation of the integer x, which is between 0 and 2 to the n. So this is going to be the basis to describe this system of n qubits. And it's known in this business as the computational basis or the classical basis. And any quantum computer can initialize each qubit, and conventionally we initialize it in the state 0. So now initially all states will be in this state 0, n-fold tensor product of zeros. And then a quantum computer can also perform unitary transformations on qubits. So this is very important. So these basically an arbitrary unitary transformation can be decomposed into more elementary 1 qubit and 2 qubit unitary transformations, and these are known as gates. So just to give you an example of a 1 qubit gate, a very famous one is called the NOT gate, which is just it's denoted by X, which is just the Pauli matrix sigma X, so 0, 1, 1, 0. So it's pretty clear that X, this NOT gate, will take the 0 into the 1, and that'll take the 1 into the 0. And so we can summarize these two results in this way, where now little x is either 0 or 1, right? So when little x is 0, we have 0, O plus 1, and this O plus is addition modulo 2. So it gives you this one. And when x is 1, we have here 1 O plus 1, which is 0. Okay, so this is an example of a 1-qubit gate. So 2-qubit gate, most famous example is the CNOT gate. So CNOT gate does this by definition. So here, x and y are both either 0 or 1. And then again, this O plus is addition modulo 2. So notice that this qubit here is the control because it doesn't change. It's x here and it's here. So the control qubit doesn't change. This qubit here is called the target qubit because it may or may not change. If the control is 1, then you see what we have here. The state of this qubit goes to 1 O plus y. In other words, the not of y. So not of y. And that's why it's called a control not, because depending on the state of the control, the target changes or doesn't change. If the control is 0, you see we have 0 O plus y, so the target doesn't change. And we'll meet this C naught a few times later in the talk. And finally, a quantum computer can perform projective measurements in this computational basis. So it can measure this operator. So in other words, if I have my quantum computer and with n qubits sitting in some general state psi, which is some linear combination of the basis states, then I can make an n qubit measurement and it'll project it to one of these basis states with probability given here. It's just the usual Born rule. And you can also have 1-qubit measurement gates. So that's it. That's basically a quantum computer. Turns out to be very useful to introduce a notion of circuit diagrams. So here we represent qubits by horizontal wires. So for example, for this basis state, n qubit basis state, we can represent it by n horizontal wires. And the convention that I'm going to follow is that the top wire will correspond to the least qubit, and then the bottom wire is the greatest. And alternatively, we can denote this n qubit state with a single wire, but then we put here n, just to remind us that this is actually an n qubit state. And then we're going to represent the gates, the unitary transformations, symbolically. So for example, this NOT gate that we talked about, we can represent it like this. And then the CNOT gate, this 2-qubit gate that we talked about. So now we need, of course, 2 wires because it's 2 qubits. And we represent like this, where this filled circle represents the control. So this qubit here would be the control qubit, which won't change. And this will be the target qubit, which may or may not change depending on the state of the control qubit. And then often in the literature, you'll, instead of seeing this, you'll see this as the notation, because this looks like an O plus, right? So this is another way of denoting control not. And finally, I should notice that time flows to the right in these diagrams. So for example, if I have a quantum state psi and I act with U and then act with V, then the corresponding circuit diagram is I start with psi, this is an n qubit state, then I apply with U and then I apply V. So one has to be careful with the orders. Okay, that's basically all you need to know about quantum computing for this talk. So currently there's actually devices out there which have around 100 qubits. They're made by IBM, Google, and others. But they're noisy. That is, they make many errors. The dream is to have devices which will have, say, 10 to the 4 qubits, and instead of being noisy, they'll be fault tolerant. So basically, they'll be that you can correct for any errors. But at the moment, that's still a dream, and it's not clear whether we'll get there and how soon if we do. But in the meantime, we can test algorithms, so-called quantum circuits, using noiseless simulators. And in the work I'll talk about here, we use the IBM Qiskit simulators. So Qiskit is the language that IBM uses to program their quantum devices. And yeah, and then these simulators can go up to about 30 qubits. Okay, so any questions about that?
I want stupid question. So in quantum computer also, we can imagine some quantum memory. In
No,
your last picture, where? No, I see.
no memory. So basically, it's the memory is going to be the qubits. So right, so you start with, yeah, so you start with a, so initially we start with all qubits in the state 0, and then we start applying unitary transformations, and the qubits are going to be in some state, and that's the memory. Um, so yeah, so this idea of state preparation is how to put those qubits in a desired state. And you could say you could store that state by storing the qubits, but in that state. But so the problem is that especially these devices here, those qubits, they don't remain coherent for very long, just for fractions of a second. So that's how long your memory is, just fractions of a second. And then once the qubits decohere, you've lost your memory. So the challenge is to make these qubits, yeah, not noisy, and also to make them long-lived, so you can have memory. Now there's other devices by other companies which have fewer qubits, but those have a longer lifetime. So so you can make a trade-off between noise, lifetime, things like this. But yeah, but right now still even the longest lifetimes are probably still, I'd say, less than a second. So so yeah, memory is very short
Okay, thank you.
for now. For now, yeah, yeah, good question. Okay, so so I'd like to turn now to, as a warm-up exercise, to the problem of preparing Dicke states. So what's a Dicke state? Dicke state, which I'll denote like this, D for Dicke, is a completely symmetric state of ones and zeros, which we already introduced. So this K tells you the number of ones, and N tells you the total number of qubits. So here, N. So if we have N qubits and K of them are ones, then the rest, N minus K, are zeros. So to give you an example, D42, so this is a state of 4 qubits and completely symmetric, where 2 of them are ones. So 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0. And you see they all have the same coefficient. It's normalized, and yeah, very simple state. Okay. But it turns out people in quantum information are interested in these kinds of states. Oh, I should say, when I write this is just a shorthand notation for 0, tensor 0, tensor 1, tensor 1. So the tensor product is understood. Yeah, so people are interested in these kinds of states. And well, we as theoretical physicists, we know how to make these states easily. We teach our students in quantum mechanics basically how to do it. You take the spin lowering operator and you act k times, and that'll give you this with k ones. So yeah, so S minus is the spin lowering operator, Sx minus Isy, where S is the total spin on for n sites or n spin halves like this. And also it turns out that these states are exact ground states of the ferromagnetic Heisenberg chain and also this Lipkin-Meshkov-Glick Hamiltonian, which is just S squared. Right, so these are very simple states, but still we'd like to know how could we prepare our quantum computer in this state. So you cannot simply implement this operation on a quantum computer because remember, a quantum computer, you can only apply unitary transformations, and S minus spin lowering operator is not unitary. So an alternative way to proceed is the following. We're going to define what I'll call a reference state, which is a state which has as many ones as we need to make this Dickey state. So we have k ones and the rest are zeros. But notice this is a very easy state to prepare on a quantum computer. All we do is we start with all the qubits in the state 0, and then we apply the not k times. And we turn k of the zeros into ones, and we make this state. So it's a very simple product state. And then what we're looking for is a unitary transformation that will take this simple product state into my Dickey state. Okay. And I'll call this the Dickey operator. And my requirements are that it be unitary so that I can implement it on a quantum computer. And it turns out, to make it simpler, that it should not depend on the value of k. So it should work for any given n for any Dickey state for any value of k. And a nice way to do this is to use recursion, and this was used in a nice paper by Birchie and Eidenbenz not too long ago. And to illustrate how that works, let's again look at an example. This is my Dickey state D42 with 2 ones. Now you notice that these 3 terms all have a 0 at the end. So I can factor out the 0, and I'm left with a state which still has 2 ones, but 1 less 0. So actually, this is a Dickey state on 3 qubits. And also, these guys all end in 1. Whoops. And if I factor out the 1, I have, again, a Dickey state with 1 less 1. So 1, 1, and 2 zeros. And this is true. And if I keep track of normalization factors, I see that this Dickey state 4,2 is 3,2,0 with this normalization. And then this guy is a D3,1 with a 1. And this is true in general. Easily show that. So the Dickey state with K1s is a sum of 2 terms. Dickey state with n minus 1 qubits, but still K1s, and 1 with K minus 1 ones with some normalization. So what I'm going to do is I'm going to apply this relation on both sides. So I'm going to replace all these Dickey states by their terms of this Dickey operator acting on the reference state. And you see, because this Dickey operator doesn't depend on the value of k, I can factor it out. And so I just have this Dickey operator on n minus 1 qubits, and I'm left with something pretty simple. And this thing I'm left with, I'm going to define it as a new operator W acting on my reference state. Okay, so I'm going to write this formula again on the next slide. Oh, and sorry, I'm going to insist that just like my Dickey operator, that this W doesn't depend on K. So for whatever K is here, it'll be the same W, only the reference state will change. Yeah, so let's write this formula again. Here it is. And so what I see then is that the Dickey operator for n qubits is given by a Dickey operator on n minus 1 qubits times identity times this W operator. So now I can just telescope this relation and I get a formula for the Dickey operator, the thing we're looking for, in terms of W. So if I can find a W that does this, then I'll be done. I'll have my Dickey operator. So yeah, it suffices to construct now the W's. So how to do that? Well, it turns out, well, we have a strategy to introduce new operators, i's, which depend not only on m, but also on another index L, in such a way that when this index is different from the one for the reference state, nothing happens. But when these indices are the same, then this I acts as W. So in other words, this operator will perform the needed transformation for a fixed value of L. And also when this index uh, is bigger than L, then it should leave this alone. It should leave it invariant. So this is so that so we're going to order these operators so that they don't interfere with each other. And then it's not hard to see that then the W will be given by a product of these i's, an ordered product. So then it suffices to construct these operators. So once we have the i's and we have the w's, and then once we have the w's, we have the u's. Okay, so let's construct the i's. So remember that IML should do the job of WM on the reference state EML. And this reference state was defined this way, this simple product state. And this W was defined in this way. So the I should take the reference state and map it to this. This looks a little complicated, but actually it's pretty simple. It turns, if you stare at this, you'll see that this state here is the same as this state here. And this state here is almost the same. The only difference is that the blue guys are swapped, and that's into the red ones. So the 0 becomes a 1, and this 1 becomes a 0. Otherwise, they're exactly the same. So in other words, this I operator only really cares about 3 qubits, the ones in color and also this one, which should always be in the state 1. And it should do this transformation. And well, to do that, we can define an angle such that the cosine is given by this, and the sine is minus that. And then a 5-minute calculation will show that this circuit, this is the C naughts that I introduced earlier, and this is a double controlled rotation. So this is our rotation, a 1 qubit rotation, but this has 2 controls. So if these 2 controls are in the state 1, then you perform a rotation on this qubit. Otherwise, it acts as identity. So it turns out that this circuit will perform exactly this job. And then that's it. We're done. Because we have the I's, which give us the W's, which give us the U's. And you
Excuse
can
me.
count the, please.
So I'm a bit lost. So this small L index is the same kind of index as your previous K.
Yes.
But why do you, I mean, I see this coefficient square root which depend on all L, and you said Wm is independent of K or L.
Yeah, so okay, so let's okay, good. So
Yes, here.
sorry. Yeah, so I defined W to be independent of K, right? So in other words, for any K here, it should do this job.
Yeah, but this Wn as a matrix will have a element which have this square root of, or there are
Yeah, so
small k appear
so
there. Yeah.
yeah, so then I defined so to construct the W's, I'm going to make it a product of these I's, and these I's do know about the K or the L, right? Because so they perform the W for a fixed L. That's what this that's what this IML does. Right. So IML knows about the K or the L, but WM doesn't care.
Because you product all of them, or
Exactly.
okay.
Yeah, exactly. Very good.
Thank you.
Yeah, very good. And so that's it. So if you compute the circuit size, it turns out to be linear in L. It's of order M times L minus M. So that's not too bad. And as an example, this is for the Dickey state 4-2, which we talked about earlier. This is the full circuit diagram. So this is the two knots, which prepares the reference state, right? It's 1, 1, 0, 0. Yeah, you didn't, the 0 should be understood here. Then this is going to be the circuit for W4, for W3, and W2. And let me just remark that we've actually looked at generalizations of this. So sort of ordinary qubit Dickey states, we've looked, which are like spin a half Dickey states. We looked at higher spin, like spin 1, spin 3 halves Dickey states and how to prepare them. We've also looked at higher rank. So instead of q bits, we could look at q dits. So basically going from SU2 to SUD. And we also have a circuit for preparing those Dickey states. Okay, so finally, let's turn to beta states. Oh gosh, running a little late. I guess I'm gonna have to maybe skip some things. But turning
Sorry,
back to
Rafael. I have one question. Sorry.
yeah,
So
sure.
I also missed one thing. So why do we want to prepare decay state?
Yeah,
Just
fair enough. Fair enough. So I didn't really explain. So for here, it's kind of like a warm up for the beta states. Um, so people in quantum information are interested in Dickey states. They use it for things. I mean, I'm not the expert, but they use it for things like um, quantum metrology, quantum sensing. Um, so there's various protocols that they're interested in, and for this,
I
they
see.
use
Okay,
Dickey
I see.
states. So
I see.
there's actually hundreds of papers on Dickey states, uh, and they've tried to create them in the lab using all sorts of using photons and using uh, superconducting qubits and you name it. There's there's a lot of interest in the community in making Dickey states. I think because they're entangled, they're non-trivial states, but they're not too complicated. So
Okay.
it's something that's doable. But I can try to give you a better answer, but yeah, it's a good question. Okay, so beta states. So here, in the beginning I told you about XXX. This is almost the same, except here I put a delta instead of 1. The solution is almost the same, just you have to insert factors of delta in this little s function that I defined. So let's suppose that these beta roots, these quasi-momenta K1 to Km are known. So the question I raised at the beginning of the talk is how to prepare the corresponding beta state. I'll denote it here now by BLM, for B for beta, L the number of sites, and M the number of overturned spins, as we talked about earlier. So actually there's been some work on this before. So there was a paper by the group at Virginia Tech in 2021. They relied on coordinate beta ansatz, but their circuit was probabilistic. In other words, it didn't always produce the beta state. Sometimes it did, sometimes it didn't. It required ancillas, that means additional qubits besides the qubits of the spin chain. And also it was limited to real beta roots. Then a year later, a group from Madrid came with a different proposal. It used instead algebraic beta ansatz, which I didn't have time to explain. Their algorithm was deterministic. However, it used something called QR decompositions, which had to be done classically and for matrices which were growing exponentially in size with M. And then there was a more recent work by Madrid people, which used kind of a hybrid algebraic and coordinate beta ansatz approach, which proposed some analytic formulas for the unitaries. So the work I want to talk about today, which, yeah, I guess I won't have much time, is this work with David, which uses coordinate beta ansatz. And this is deterministic. It doesn't use any ancillas and doesn't require any of these QR decompositions. So, so here it's convenient to denote the beta states in this way. So, so here I'm summing over all W's, which are in the set of permutations of M1s and L minus M zeros. So, for example, B42 would be like this. So it looks like the Dickey state, except in the Dickey state, all the coefficients would be the same. Here we have different coefficients depending on the state. And these coefficients are going to be given by the formula of beta, beta's coordinate beta ansatz wave function that I showed you at the beginning of the talk. So here, these x's are now the positions of the ones in the w's. So where these ones are, that's what the x's are. The main point is that these coefficients, there's L choose M of them, and they're known. Because once we know the beta roots, then we know what these numbers are, and so we know these coefficients. And the task is how to prepare this state on a quantum computer. And yeah, I guess I'm not going to have time to explain. Basically, it's a generalization of the Dickey circuit I showed you earlier. The main idea is that we're going to use sorry. Yeah, we're going to use a recursion and we're going to, yeah, so I'm sorry, I'll have to skip all this, but it's very similar to the way we did Dickey states. And so, for example, in the case of the beta state with 4,2, this is the circuit. So again, this is going to be the reference state. We have a product of W's. And yeah, except for these the angles and these gates, it's the same as for the Dickey states. So so similar logic, we can get the beta state. However, the circuit size is going to be much bigger. It's going to be of order L choose M, and which is roughly the number of free parameters, right? The number of coefficients in the vector. So we expect that this will be optimal. But still, that's not very good, because if I now take the maximum value of M, namely L over 2, then L choose L over 2 is the order of 2 to the L. So the size of the circuit, the number of gates, is going to go exponentially with the size of the circuit, with the size of the system. So this is not very good. So that's the bad news. Okay, so to conclude, this circuit that we found works for any U1 invariant model. So here I was talking about the closed periodic chain, but it also works for the open chain. Something which is kind of fun is that we can now estimate beta roots by a variational approach using these beta states as trial states. So if you remember from the first part of the talk, beta reduced the problem to solving a system of polynomial equations, in the case of xxx, or polynomial, and otherwise more complicated sets of equations. And that's still a hard problem. It's hard to do. And we're always looking for new ways of solving beta equations. And well, this is perhaps one new way of solving beta equations on a quantum computer. And David and I have a recent paper on that. But as I said, the size and the depth of the circuit are exponentially big. It would be nice if we could find ways to reduce them. There's been a lot of recent work, for example, by this group here, using additional qubits, ancillas, intermediate measurements, and so-called feed-forward operations, which can be used to reduce the depth of a circuit. So in this paper, they actually proposed another way of preparing Dickey states, not beta states, but Dickey states, using circuits of shorter depth, so shorter than the circuit I showed you, but it exploits these kinds of ideas. And also, there's a recent paper by this group which slightly reduced the size of our circuit. And also, we know that there's coordinate beta ansatz for higher spin chains and also for higher rank chains. So one could try to generalize this algorithm to such models. And even maybe here we always were assuming U1 invariance. So one could even think about integrable models or models without U1 symmetry. And with this, I'll stop. So thank you very much. Yeah,
Thank you,
I'm sorry I
Rafael.
had to go. I'm sorry I had to go fast to that last part, but I will share my slides with the secretary. And then if you have any questions about that, please feel free to, if I don't answer now, feel free to answer to reach me by email, and I'll be happy to try to explain.
Okay, thank you. Yeah, any questions? Please ask any questions. I have one question. So I think there is maybe uh, not related to your talk directly, but you know, we can define the computational complexity
Mm,
in then can you measure that in your some integrable I mean okay, so let me ask again. So I think the the integrable spin chain, there's the integrable. So maybe little far from complexity in some sense. So can we, if we compute the simply just the if we count number of gate or in your circuit,
right.
then
So
what happened? Yeah, yeah.
yeah, so
Can you
I
comment
think
anything?
that yeah, I think that would be a reasonable number of way of quantifying, yeah, the complexity of the circuit, no, is the size of the circuit. And yeah,
Uh,
it's exponential. So yeah, it's very bad. It's as almost as bad as can be. So and that's quite a disappointment. So actually David and I are still kind of optimistic, or maybe not optimistic, but we feel that there should be a better way to do things. You see, in this circuit, we didn't really exploit integrability at all. Um, we
mm,
basically, if you give me these coefficients, f of w, this circuit will prepare the state. So the role of integrability is that it tells you what the so we know what the coefficients are if we know the solutions of the Bethe equations, but it doesn't give you any simplification of the circuit. And we integrable people, we have this prejudice that integrable models should be nicer, right? Uh, so it'd be nice to have a circuit that really takes advantage of the integrability. And this circuit doesn't do it. Uh, Actually, the ones that the Madrid group was trying using algebraic beta ansatz. So conceptually, that's nicer, right? Because then that principle would exploit the integrability of the circuit. But then they had other problems. So I think this is still a wide open problem. This is not the final say. This is not the end of the story. And there should be a nicer story.
I see. Okay, thank you. Okay, any other questions?
Perhaps another question, but just I'd like to really thank you for your talk, also especially including those first a few slides for late Professor Theory. I really appreciate it.
Oh, thank you. Thank you.
And also, this is not a question, but I just want to say that this was the most helpful seminar I have ever heard about quantum computing. I mean,
Oh, thank
yeah,
you. Thank you. So I'm not an expert. I'm still learning, but I'm having a lot of fun. So,
yeah.
and it's a very active subject. Um, so yeah, you're a young person, so I encourage you to, if you're interested, to look into it. It's really a lot of fun.
Thanks for the nice summary.
Okay, thank you.
Okay, then let's thank again the Rafael. Yeah, thank you.
Okay, thank you all. Thank you, Minkyu.
Oh yeah, welcome. Yeah.
Okay, and again, any
By the way,
questions, feel free to reach out.
mhm. Uh, yeah. Okay, so our seminar is over. Yeah, just yeah. I think that yeah maybe I will email you again later. But recently I realized that maybe you heard about that. Some black hole physics guys also studying Bethe equation. Did you hear about that?
No, by the way, we're still recorded. Did you
Yeah.
want to keep?
So when
You want
he
to keep?
computes
Did you?
some
Did you want to? Minkyu, did you want to turn off the recording?
yeah. Maybe how to
There should be a button.
I'm not um yeah, so our secretary is doing that. So I see. Um, I don't know how to do that. Yeah, but
Oh, okay.
yeah. But anyway, I heard about that. So and that will be quite nice. Maybe I will email you later. Okay.
Oh, do you have? Is there a paper?
Just there are many paper, not my paper, but just
But there are
I
also.
just feel I just feeling the if some integrability expert try to solve that, then that will be very helpful because I think the many black hole guys really do not understand how to solve the completely Bethe equations in some sense, not rational case, maybe elliptic case. Yeah, but
Elliptic case. Wow.
yeah,
Okay. I'm not sure I can either. That's hard. Elliptic
yeah,
is very.
I know. Yeah, that's very hard. But maybe anyway, the like in the 2002, when Minahan Zarembo first found the spin chains, then like you and Changlim, just going to that direction and made some development. Very similarly, I think for example, the Professor Juno asked you some question about the young guys, the new faculty in Sogang. Then